The AI model Claude Opus 5 recently set a record on a grueling new software engineering benchmark called SlopCodeBench. This chart shows strict pass rates across a 17-checkpoint track. Opus 5 achieved a 24% success rate, 4 times higher than competing models stalling at 6%. But at checkpoint 5, Opus 5 introduced a critical software defect and permanently halted. This failure occurred across all tested models. They accumulated defects steadily until they permanently stalled, even on tasks explicitly labeled as easy difficulty. This suggests a gap between how these models perform in a vacuum versus how they handle the friction of a continuous project. They can win short sprints, but they appear to struggle with endurance runs. The software industry currently relies on benchmarks like SWBench to evaluate coding models, but these are typically single-shot generation tests. They ask a model to solve one isolated problem at a time. In many cases, this provides an incomplete signal of how much autonomy a model actually possesses. Real-world software engineering is rarely that static. Developers are not handed the entire architectural blueprint up front. Requirements shift, and new features must be integrated into existing code. This creates a tension between solving an isolated task and maintaining the structural integrity of a codebase over time. Until a model can survive long-horizon incremental evolution, the goal of fully autonomous lights-out coding agents remains technically unproven. SlopCodeBench tests this capacity by actively hiding requirements from the model. This diagram represents a codebase architecture. The benchmark divulges instructions strictly one checkpoint at a time. The model builds the system blind to future architectural requirements. In the circuit eval challenge, requirements move from a simple command line interface to complex vector math, slicing, and indexing. The model must evolve its existing architecture to accommodate these new rules, completely blind to what the following checkpoints will demand. To maintain the integrity of the test, each new checkpoint is run in a completely fresh context window. This incremental reveal mimics how software development actually operates under shifting product requirements. To measure success under these conditions, the benchmark uses a high bar evaluation called the strict pass. A strict pass requires that the new code works, and every inherited regression test from previous checkpoints remains functional. This creates a chain of failure. If a model introduces a defect in checkpoint 4, that code carries forward, and all subsequent checkpoints fail automatically. The researchers found that models rarely fix a broken evaluation case once the underlying architecture begins to degrade. Across 9 parallel test runs, not a single model reached the end of any challenge with a perfect pass rate. The data suggests that current models struggle to preserve the context of past architectural decisions while building new features. To understand why Opus 5 achieved a 24% pass rate before stalling, we have to look at its generation strategy. The model attempted to maintain correctness through sheer overwhelming output volume, essentially attempting to outcode the rapidly shifting requirements. This dashboard compares total code produced. Opus 5 fired over 29,000 lines of code, more than triple the 9,000 lines written by competing models. The function count shows a similar trend, generating 5 times the number of individual functions compared to Opus 4.8. Rather than refactoring the existing code, the model relied on thousands of small, verbose functions to patch new requirements into the system. A significant portion of this volume was dedicated to writing more tests, rather than streamlining the production logic. Opus 5 achieved its temporary success by overwhelming the codebase with raw volume, a strategy that eventually resulted in complexity the model could not resolve. This volume-heavy strategy led to a rapid increase in technical debt, which the benchmark quantifies as SLOP. 93% of lines generated by Opus 5 triggered a SLOP rule. These rules track indicators of poor code quality, like excessive verbosity. The verbosity metric climbs steadily, moving from 65% at checkpoint 1 to 80% by checkpoint 8. We saw a different failure mode in Opus 4.8, where code duplication rates jumped from 4.6% to nearly 17%. This spike in duplication typically occurs when new requirements begin to conflict with the model's initial design choices. While high volume can buy short-term passes, it eventually creates a level of technical debt that makes further progress impossible. Looking at the financial data from this 6-hour test run provides a clear picture of the economic reality. This graph plots the relationship between compute cost and correctness. Even as spending increased, the models reached a point where more compute did not lead to higher completion rates. As the report concludes, every dollar bought correctness. Nobody bought enough of it. This indicates that architectural degradation is a structural challenge that cannot be solved simply by increasing compute or spending. For engineers and organizations looking to deploy AI agents in production, the findings from SlopCodeBench are significant. While current models perform well on many one-shot generation tasks, SlopCodeBench suggests that multi-turn maintenance is a different class of problem. If the highest performing model available tops out at a 24% pass rate in a controlled environment, it raises serious questions about the reliability of unattended AI agents in real-world repositories. The evidence suggests that autonomous software engineering remains out of reach until models can demonstrably survive the friction of long-horizon evolution.